Good afternoon. I'm shooting from Satellite Technology and Research Center in National University of Singapore. My presentation title is Space Solar Power Millimeter Wave Mid-Air Recharging Performance Analysis, Atmospheric Rain and Cloud Attenuations. So if you have following the news for the last 12 months, we have experienced the worst bushfire in Australia and also one of the worst wildfire in Northern California. And then in the China, we also have the irregular weather storms that cause multiple city experience river floods. And also last few weeks ago, there was this news that report about the glacier in the Antarctica has been broken free. So all these events could be either directly or indirectly related to the global warming. And in the future, it might result in a huge economy loss. So that's one question is that, what are the steps that we could take to respond to these issues? So for the aviation industry, NASA has proposed a technology development roadmap to lower the carbon emissions by the commercial aircraft. So for the first phase is to improve the fuel efficiency by 2020. This can be achieved by the more electric aircraft type that utilize the combination of the jet fuel and batteries, and also the advanced propulsion units. And then the next phase is to achieve the zero carbon emissions by 2030. So recently, Airbus also has announced 3 new concept carbon zero emission aircraft that are using the hydrogen fuel cell as energy. And they expect that the first prototype aircraft can be seen by 2035. And then finally is to achieve the 50% of the carbon emission reductions by 2050 as the current is as compared to the current stage. So to achieve this target, several meetings ago, we also have proposed all-electric aircraft. Basically, the all-electric aircraft, or AEA, we call it here, use the battery only as the energy source. But if you only are using the battery as the energy source, there's still a lot of challenges because right now, the energy capacity of the commercial battery is very low when compared to the jet fuel. So here is talking about the lithium ions. So if you say that you want to increasing the battery size so that we can increasing the overall energy capacity so that our aircraft can fly longer durations, but actually you might increasing the overall payload weights that affect the overall aircraft weights and then reduce the total flight range. So we have conducted several investigation study to look for what are the solutions. So the first one, we look into the available new battery technologies in the laboratories. So we find there's a few higher energy capacity batteries that over 1800 watt hour per kilogram. So these are the lithium sulfur, lithium airs that is very suitable for all electric aircraft types. Then we also propose the mid-air recharging methods via the wireless power transfer. So in our study, we also found that actually we don't need the 24/7 mid-air recharging availabilities. So we can have a 20 minutes of backup for every 45 minutes of the mid-air recharging availability. And we also included the ground-based inductive power transfer when the aircraft is on the ground and taxi on the runway. And the other challenges are, what is the AEA tracking accuracy required by the space solar power satellite constellation so that this satellite can accurately beam the microwave energy down to the AEA rectangle. So based on our study, commercial sensor is good enough to achieve this kind of accuracy requirements. So there are still other questions has been coming out. For example, what is the loss due to attenuations or due to the Earth environmental attenuations? So which is the focus of these presentations. So in this objective is consider that our wireless power transfer is a millimeter wave, which is 30 gigahertz frequency. So we would like to study the impact of the Earth environmental attenuations. So here the Earth environmental attenuation including the Earth atmosphere, rain, cloud, ionosphere, and troposphere attenuations. And we also study the attenuations with respect to the different flight altitude or flight levels, and also the latitude regions or locations. So first, our total attenuation model will be based on the International Telecommunication Union's recommendations or the ITUs. So the equation over here can see is that the total attenuation is a function of atmospherics, rain, cloud, and the troposphere attenuations. But ionosphere is not included here because for ITU, they have a different way of doing the evaluation on the ionosphere attenuations. But for our study, we also exclude both ionosphere and troposphere attenuations because they only impact the frequency between 100 megahertz to 12 gigahertz and 4 gigahertz to 20 gigahertz, while our frequency is 30 gigahertz. Because of time constraints, I won't go through details in all the equations. I will simply go through some important parameters. So the most important parameters are the altitudes, location, seasons of the dates. So, and then also the frequency. So the first three will impact our modeling on the pressure, temperatures, and the water vapor. So the modeling here is, I mean, the atmospheric modelings. And then the next two are the slant distance, which is the approximate of the true signal traveling distance due to that across a different layer of the atmosphere, because at a different layer we have a different air density, pressure, temperatures that will result in the different value of the refraction index. And then the dry air and the water vapor attenuation are the components of the atmospheric attenuation. So basically, if you look at the atmospheric attenuation over here, the gamma is a specific attenuation, so it consists of the dry air and the water vapors. So if you look at the figures on the right here, you can see that the pressure, temperature with respect to altitudes is non-linear and somewhat discontinuous. So usually we just slice the atmosphere into multiple layers. So in each layer, we can do a more accurate modeling of the temperature between the zones so that we can calculate the slant distance, refraction angles, and etc. And then the next set of parameters are for the rain attenuation and cloud attenuations. Basically, for rain and cloud attenuations, most of the parameters are available either in the form of coefficients, for example, the rain attenuation coefficients, cloud liquid water specific attenuation coefficients, or available inside the data sets, like the monthly rain rates, rain cloud thickness, and also the total communal contents of the liquid waters. For the cloud height is a fixed value in these recommendations. And for the polarization tube angle, it will depend on our type of our signal polarizations. So for circular polarizations, since the magnitude of X and Y is 1, so if you take the arctan of the Y over X, then you get a 45 degrees. So this is the overview of the rain and cloud attenuations. So for the rain attenuations, it is similar to the atmospheric attenuations. For the cloud attenuation is slightly different. It's more towards a function of the elevation angle. But this one I won't talk details over here. You can refer to the paper and also the reference. So once we have the atmospheric rain and cloud attenuations model, then we can begin our simulation study. So the first thing to do is we would like to choose the highest average rain rates months. So this month is fall in the July based on the data sets. And then we consider 3 latitude region, which is based on the ITU atmospheric modeling. So for the low altitude, represent the tropicals or equator areas. Mid latitude is subtropical up to somewhere in between temperate areas. And high latitude is above the 45 degrees of latitude or lower than 45 degrees of latitude. So for each region, we choose location where we have the highest rain rates, and the rain count is above 4.2 kilometers. So this represents the Tibet areas, Bolivia. Unfortunately, for the Greenland, it has the highest rain rates, but the rain cloud is lower than 4.3 kilometers. So for the rain attenuation, high altitude region is not included. And then for the all-electric aircraft altitude, we chose between 16,000 to 41,000 feet. So this is based on the survey that for the commercial turboprop and turboprop and cruise altitude, they are usually fall between this range. And then the transmission frequency once again is 30 gigahertz. And then for the space solar power satellite constellation configurations, this will be based on our previous studies. So it will be 750 kilometers altitude sun-synchronous orbits. So now we look into the atmospheric attenuation. The first one will be at a low altitude. So if you look at the low elevation angle regions, you can see that the atmospheric attenuation is very high, can up to 3 decibels. But fortunately for the current millimeter wave antenna technologies, so the highest available field of view is about 120 degrees, or half cone FOV is about 60 degrees. So we take the 90 minus 60 degrees, then we can get our minimum elevation angle is about 30 degrees. So if we start from the 30 degrees, then the atmospheric attenuation is about less than 0.1 decibel. It is low, but it's not negligible. So if you go into the high altitude area, 35,000 feet, 41,000 feet, the overall atmospheric attenuation is much lower, which is expected. So once again, we just only look at the elevation angle larger than 30 degrees. So the atmospheric attenuation is about less than 0.05 decibels. And next, we move into the rain attenuation. So here we consider two scenarios. The first scenario is light or medium rains. So it's on the left. So we consider that the rainfall is evenly distributed over 30 days. On the right is the heavy and storm scenario. So the rainfall are more focusing on 7 days between the months. So when we have a heavy rain, actually the attenuation is quite high. But if you look at the elevation larger than 30 degrees, then the rain attenuation is about 0.035 decibel or lower. So in overall, it's still lower than the atmospheric attenuations. So if you move into the cloud attenuations, we can see is that in overall, the cloud attenuation is very low, but it's not negligible. So if we look at the elevation larger than 30 degrees, so the cloud attenuation is about 0.015 decibels. So although it's low, but it's not negligible. So in the conclusions, we have studied the impact of the atmospheric rain and cloud attenuations of the wireless power transfer at 30 gigahertz frequencies. And once again, we do not include the ionospheric and the tropospheric attenuations, because for the ionospheric attenuation, it only impact the frequency between 100 megahertz to 12 gigahertz. Also for the tropospheric attenuations, only impact the frequency at between 4 to 20 gigahertz. Overall, the atmospheric attenuation still contribute the highest. And in general, when we design the transmitter and the receiver of the wireless power transfer between the all-electric aircraft and the space solar power satellite constellations, then we need to take into account that there will be additional 0.15 degree of the attenuation due to the atmospheric rain and cloud, especially during the link budget calculations. So definitely there is still some work that has to be done. So for example, what is the average minimum and the maximum of the total attenuations when a commercial aircraft fly from point A to point B? And what's the energies that needed to supply to the aircraft when flying between 2 points? Especially we know that when the distance between aircraft and satellite change over the times, and so that what kind of design and implementation strategy additional that need to be considered. And then the other one is, what is the size of the space solar power constellations that required to support AEA networks? So whether it's only one constellation is enough or multiple constellations across the different altitudes. And then the third one will be, what are the other factors that could impact the space solar power constellation implementation costs? So what are the steps that we can take to minimize these costs or to minimize these impacts? So this is the end of my presentations, and thank you very much. If you have any questions, then you can email me or email Dr. Zekavat. Thank you.